This example uses the Lorentz velocity transformation. If we let the Earth and the spaceship reference frames be S and S prime respectively, then their velocity, their relative velocity is, the velocity U is 0.9. That of C. S is, again, the Earth reference frame. S prime is the spaceship. And for the spaceship, we are given that the velocity of the spaceship is Vx, which is 0.950 c relative to S, and we want to find in part A the probe velocity. So this is of the scout ship relative to S. Part A, we want to find the probe velocity, so Vx equals Vx prime plus U over 1 plus U Vx prime over c squared, where Vx prime is the speed relative to the spaceship. So we get 0.7 c plus 0.9 c over 1 plus 0.9 c times 0.7 c over c squared. Notice that we get a c in the denominator left from the cancellations, and we get about 0.982 c for the probe velocity relative to the Earth. And for part B, if we want to find the scout ship velocity relative to the spaceship, then that's Vx prime equals Vx minus U over 1 minus UVx over c squared, which equals 0.95 c minus 0.9 c over 1 minus 0.9 c times 0.95 c over c squared, and that gives us 0.345 c. And you'll see that obviously there's a huge difference between those two speeds, which is, again, why relativity is very important and which reference frame we are using. Notice that this is somewhat similar to what we used before in terms of the Doppler